Okay, in this video we are going to explore the position, velocity, and acceleration versus time plots. So first off, it's important to understand what we mean by versus time plots. So anytime we say something versus something, it's always our vertical versus our horizontal, or the dependent variable versus the independent variable. So a position versus time graph would look something like this. Let's say we have one-dimensional motion here. So this is our x position. The units will be meters, and this is our time, and the units will be seconds. And let's say we just have a plot of position versus time that looks something like this. Now, if we look at the slope of this graph, then their slope is going to be the rise over the run, right? So our rise will be a change in the x position, so this will be delta x, divided by our run, which will be a change in the time, delta t. And the units of this will be in units of displacement, or in meters, units of time are in seconds, so we have meters per second. And this is what we defined to be our velocity earlier. So the slope of a position versus time graph is equal to the velocity. So if we have here, we have a positive slope corresponds to a positive velocity. A zero slope corresponds to a zero velocity, and a negative slope is a negative velocity. And we could also get the values from it. Let's say that this was just this is 2 meters here, and let's say this is 1 second. Then the slope here is going to be our rise is 2, our run is 1, and so the velocity in this region is equal to 2 meters per 1 second. So 2 meters per second is our velocity right there. And this is the average velocity over this interval, but we see that the slope remains constant, and so therefore our velocity remains constant as well. Our velocity changes here. Now the slope is 0, so the velocity is 0. So it's averaged over the whole interval. If we want to get the instantaneous velocity, we would just take 2 points very close together, and we would see here, since this is constant, our instantaneous velocity in this little region is the same as this average velocity here. But that's how we could get it. So that's a position versus time. Now let's look at a velocity versus time graph. So if we plot velocity on the vertical axis, so here's velocity in meters per second, and this is time in seconds, and we'll just say that we have something very similar here. Then the slope of this would be equal to our change in velocity with time. And the units of this would be in meters per second, which is the same as meters per second squared. And so this is what we define to be the acceleration. So the slope of a velocity versus time graph is acceleration. So we had some positive acceleration here, some zero acceleration here, and some negative acceleration there. Note here that the velocity remained constant, or not constant, but positive the whole time. Just because the acceleration was negative here didn't mean the velocity was negative. If we had a negative velocity, it would be shown down here. This would have been a negative velocity. Let's also explore a little bit the area under here. So let's say we wanted to find the area underneath this curve here. Now the area, we could break this up into 3 composite shapes. We'd have a triangle here, a rectangle here, and another triangle here. And the units of this area, let's say here we have the area. The height is going to be in meters per second. The base is going to be in seconds. So this is the units of the area will be in meters per second times seconds, which is meters. And so we can infer from this that the area under a velocity versus time graph is the displacement. And so if I want to find out how far a particle displaces, let's say here from time equal to 0 to time equal to 1 second, then that would be the same as this area right here. that would be the displacement after this amount of time. If I wanted to find the displacement after this amount of time, then I would take the entire area here, okay, and then etc. and so on. And any area above the time axis would be a positive area. Down here, this would be considered a negative area, so it would be a negative displacement as it moves back towards the origin there. So the slope of velocity versus time is acceleration, and the area under a velocity versus time graph is the displacement. And let's also look at an acceleration versus time graph. So let's say we have acceleration here in meters per second squared, and then we have time in seconds, and I'll just have the same shape here. We won't really deal with the slope of acceleration versus time. This is something called a jerk, but that's beyond the scope of the class. But nonetheless, we can still look at the area here. If I have a similar shape, similar composite shape, two triangles and a rectangle, in the area here under acceleration versus time graph would have units of meters per second squared times seconds, and this is equal to meters per second. And so the area under an acceleration versus time graph is velocity. And so if I wanted to find out, if I have a particle starting out here at time equals 0, and I want to find, and this would be its instantaneous velocity, what is the velocity at time 1 right here, then that would be the area of this underneath here. If I wanted to find the area at time 2, then I'd have this whole area all here, etc. Right? And the same thing with if it goes below the time axis, it would be a negative area, and it would decrease the velocity. So that would be how I can find the instantaneous velocity at each of these points. So just to kind of recap, the slope of position versus time is velocity. Slope of velocity versus time is acceleration. The area under a velocity versus time graph is displacement. And the area under an acceleration versus time graph is velocity, instantaneous velocity. So let's do a couple examples here. We'll have a given position versus time graph, and we'll sketch the corresponding velocity and acceleration versus time graphs. And by the way, we could find the values of the velocity as well, just like we had finding the value of, we could find the value of the acceleration as well. Let's say in the velocity versus time graph, this went up to 2 meters per second over 1 second. Very similar to how we did this in the position versus time graph. We would have had an acceleration of 2 meters per second squared right there. So we can get quantitative values, but let's just do some qualitative graphs here. So let's say that we have, I don't know, we'll stick with kind of this shape we've been drawing, so something like this. Let's say that we have an object that moves this way in one-dimensional motion along the x-axis. Now, if we're given this, then we can plot the corresponding velocity in the x direction and acceleration in the x direction graphs versus time. So these are all versus time here. This is our time axis. So given this position versus time, and noting that the slope of position versus time is velocity, so the value of this slope would be the value of the velocity. And so this slope, actually I drew it at 1, so the slope of this yellow line here was 1, and so the slope of this, or the value of this, would be 1. And we said the slope is a constant 1, and so the value is a constant 1, so this is the value here, and it goes up until about 4 seconds. It's always best to have these right on top of each other so we can line them up, and so this lines up just like this. So the slope value here became the velocity value here. And then we have And this region, now we have a slope of 0. So that means that our velocity is 0. And so then for the next, from 4 seconds to 12 seconds, we have a velocity of 0. So the value of the velocity is equal to 0, meaning that the particle is just sitting there staying still. Had some positive velocity here, some zero velocity, positive velocity from 0 to 4 seconds, zero velocity from 4 to 12 seconds, and then we look in this last region here, and the slope is a -1. This goes down 4 and over 4, so the slope was a -1, meaning that the value of the velocity will be a -1. And so then from 12 to 16 seconds, we will have a value of the velocity being -1. Okay, so the corresponding, so our position versus time graph given there, the corresponding velocity versus time graph looks like that. Don't worry about these little breaks right here. Don't worry about this. Just the regions from 0 to 2, 2 to 14, or sorry, 0 to 4, 4 to 12, and 12 to 16 are important. And then drawing the acceleration versus time graph, we just do the same thing. And this one's not quite as exciting because we had the slope of velocity versus time was 0 here, slope of velocity versus time was 0 here, and slope of velocity versus time was 0 here. So the slope was always 0. And since the slope of velocity versus time is the value of the acceleration, our acceleration was 0 the whole time. Now there actually was some acceleration going on in these little red regions here, but I'm not interested in you plotting those. So we'll just plot our acceleration versus time like this because we had constant velocity. Okay, let's try another one. Let's say that we have something maybe given like this, and so we have some curve here in the position versus time, and then maybe this is so that's some curve region. We'll say the curving is constant too, and then this is a straight line, and then maybe flat straight line like this, and then some curve region again, something like this. So these are straight, constant slope. These are curved here. Let me draw this a little bit more curved, something like that. So how does this look on the velocity versus time graph? Well, for the slope of position versus time is velocity, and so we have the slope here was 0, and the slope is not constant in this region. So the slope was 0 here, and the slope was positive here. So this means the value of velocity versus of the velocity was changing. 0 slope, positive slope. I'm not exactly sure what the slope is, so I'll make this more qualitative. But if we start out with a 0 slope, we'll have a 0 value. And then at 4 seconds, we should have a positive value, maybe something like this. And so then if we assume that this slope is changing at a constant rate, this will be a straight line. So, which is what I told you guys, this is changing at a constant rate. Okay, so we started with a 0 slope, ended up with a positive slope. So we started with a 0 value, ended up with a positive value. And then we have in this next region here, we have a constant slope and a positive value. So I should have a constant value, right? A constant positive slope would relate to a constant positive value. So from 4 to 6 seconds, it might look something like this. So positive constant slope translates to a positive constant value. And then this next region here, we have 0 slope. And so then the value of velocity versus time must be 0. So from 6 to 10 seconds, we have 0 velocity. Looks something like this. And again, don't bother with what's going on right here. Next, we have a constant negative slope. So I should have a constant negative value. So something like this, maybe a constant negative value. And then lastly, we have, well, I had a negative slope here, right? This was a negative slope, and then the slope becomes 0. So I should start out with a negative value and then end up with a 0 value over here. So, and I told you that this slope was constantly changing at the same rate, so this ends up being a straight line, and we have something like this. So we have here, again, just the value of the slope becomes the value of the velocity. So this is the corresponding velocity versus time graph for this position versus time. And the acceleration, again, we do the same thing, and we have the slope here was a positive constant value, and so then the acceleration was some positive constant value as well. I could actually get, this was not quantitative, so I can't really express this quantitatively either, so just kind of qualitatively here, I'll just say that the acceleration is something like this. And then we have a 0 slope, and another 0 slope, and another 0 slope. So we have 0 acceleration in all of these. So all the way from 4 to 12 seconds, we had 0 acceleration. And then again, we have a positive constant slope. So we have a positive constant value from 12 to 16 seconds, something like this. Okay, so there would be the corresponding acceleration versus time graph. Lastly, I want to look at maybe a ball being thrown up in the air. And so the path of a ball being thrown up in the air might look something, it would be curved the entire time, and it might look something like this. Okay, and it should be even on both sides, to parabolic. So right in the center here is at 8 seconds. Now if I want to plot the velocity versus time graph, I would note here that we have a positive velocity, right? We have a positive slope, so positive velocity, and then it becomes a 0 slope, so 0 velocity, and over here it's a negative slope, so a negative velocity. So I need to have something starting out positive, maybe up here, and then at 8 seconds it should be 0, and then at 16 seconds we should have negative. And this will actually be negative the same magnitude as it was positive over here. We can see if it's parabolic, it'll fit that description, so we go down to there. And so we see the velocity versus time graph would be a straight line down like this. As long as this as long as it's parabolic, then this curve is always changing. The slope is always changing at the same rate, and we'll discuss this in future videos, that it is in fact parabolic. And so then this is always changing, this slope is always changing at the same rate, and so therefore we end up with a value always changing at the same rate, so a constant slope. And so then therefore we have some interesting things to point out here. When it's first thrown up, when it leaves your hand, it had a positive velocity. Then it reaches its highest point, it has a 0 velocity, and then it gets, right before it gets caught, it has a negative velocity here. And the acceleration of this would just be, we have here a negative constant slope would correspond to a negative constant value, and I'm just doing this qualitatively. Let's say that we have our acceleration here. The acceleration here for a ball thrown upwards is actually going to be downwards gravity, so this will be negative 9.8 meters per second squared, but we'll discuss this in future videos. So here's position versus time, velocity versus time, acceleration versus time plots for a ball being thrown up in the air, and just in general plots.